Let's go ahead and get started. Welcome everybody back to Friday. Second lecture of probability day. Going to go over some more examples, some simulation. Does anybody have any questions about the probability that we had last time? Any questions about the class or anything? Alright, well, up here, quiz and homework assigned. Both are due next Friday, so you have a week to work on that. And then next week, I'll be here for Monday, but Wednesday there'll be a new like teacher professor in here to teach you guys for a little bit. So I'll be out for a little bit, but I'll still be here if you need to email or ask questions or stuff like that. So let's go ahead and get started. So one thing I wanted to talk about today, we talked about independence last time, and I want to talk about this idea of mutually exclusive or disjoint events. So in here, it's not the same as independence. It's actually, or even the opposite of. They're two different types of concepts here. And so independence explores how probabilities are changed when two or more events occur in one trial or one test. So events A and B are mutually exclusive or disjoint if they cannot occur simultaneously during one statistical trial, experiment, or observation. So one thing like that I could think of is like events A and B. So I cannot both be teaching in this classroom and be teaching in a classroom across Virginia Tech at the same time. These two events are disjoint. They can't happen. They can't happen at the same time. And so the intersection between the events, if you're thinking about it in the Venn diagram sense, where we have our black box here, S, we have events A right here and B right here. They have nothing in common between the two of them, and thus their intersection is 0. There's no overlap. And because of probability, we can do P of A union B, instead of it being P of A plus P of B minus P of A and B. This piece right here can just get scratched out to just leave P of A and B, A or B, is P of A plus P of B. And so you can kind of see it on the slide here where the circles are completely apart and they don't have any intersection or common ground between the two of them. So one example you can think about for this is for lottery numbers. So suppose I have one event, and we're talking about the 3 lottery numbers where they can range from 0, 0, 0 to 9, 9, 9. And so A is the event that all 3 are the same. And B is that the first and last digits are different. And so just by even looking at this, if you remember from last time, the only 10 scenarios of this are from 0, 0, 0, 1, 1, 1. I'll write them out here just to be concrete about it. And so in these 10 cases, you do not have a single one of these where the first digit and the last digit are different. Because of course, to have all 3 be the same, you need to have the first and last be the same as well. And so these 2 events are mutually exclusive or disjoint. So if I were to have, a sample space, S over here for this problem, and A would be pretty tiny because it only happens 1 out of 100 times. So this will be A. And you have B, where the first and last are different, be a larger part because that can happen a whole bunch of times throughout. Any questions? And so this leads to the addition rule, where we have, I've said P of A union B. It's the same thing as P of A or B. So we discussed and last time with the intersection between the two. But U is for the union. And so the Venn diagram that I have up there, that you can think about it, it just, the common space in between, you incorporate that. And so the mathematics behind it is that you add the first circle plus the second one and minus the in-between, because if you think about it, what we have is this Venn diagram S, and then A, B. Well, you can see if I add these two together, I'm getting this much space, and then this much space. And so I'm kind of double counting the middle portion. And so essentially what you need to do is subtract out one of the middle portion there. And that's why, at least in Venn diagram explanation, the P of A or B is P of A plus P of B minus P of A and B. However, like what we just saw, for mutually exclusive events, this part's 0. So I mean, this formula applies for all of these A and B events, but you can just shorten it for mutually exclusive ones. And we'll see some use of the addition rule on the homework, and also, I think, on some examples today. Well, next I'd like to talk about conditional probability a little bit. So we talked about conditional probability last time with already knowing what you have information for A or for B. But here's the precise mathematical formula for it. And so generally, P of B given A is P of A and B over P of A. And so what this is saying is, given all of the events that happen in P of A, what's the amount that intersects? So in the Venn diagram layout, A and B, essentially you're taking all of this right here, all these black lines across, and you're finding out what percentage of the portion is with this middle part in here. So essentially, it's this part over this part. I think pictures are a little understanding, just to see where we get these equations from. And so you can swap P of A and P of B back and forth, just to get, this is generally for any A or B, and so it works in the converse as well. And so we'll be using that on this example here. So this is going back to the example where I'm picking on one of you to answer a question. What probability was it for the first question? And so if we don't have any prior information, P of A is just 1 out of 50, or 1 out of how many students there are in this room. And if they're selected to answer any one of the questions, since there's 3, it would be P of B is 3 out of 50. And since A is a subset of B, meaning, P of A and B is a subset within A. It's contained inside of A. And so in this case, to figure out if she was already selected for one of the questions, the ability that it's question 1 kind of makes sense. It's just 1 out of 3. Because it would just be 1 out of 50 divided by 3 out of 50. Does that make sense? Yes? Okay. So overall, students sometimes confuse the definitions of independent and mutually exclusive events. So when they're mutually exclusive, when one happens, it turns the probability of the other one to 0. And when they're independent and one happens, it leaves the probability of the other alone. And so here's just a common way just to think about it. And so we have the first two rows are, the first one's mutually exclusive, the second one's independent. And so you still need to have this multiplication between P of A and P of B for that portion of independence. And so when they're mutually exclusive, there's absolutely no common ground. But when they're independent, there could be common ground, but it would be P of A times P of B. So whenever you're doing these questions, you figure out words like, I'll say mutually exclusive or independent, or just generally I don't mention any of that. You can use this as a way of what formula to use in that case. And we'll go through some examples, and Monday will be in a class activity going through some probabilities. So if you guys want some more practice doing that, we will have more practice doing these problems. It'll make more sense going from there. So I just want to talk about sampling with and without replacement. We talked a little bit about this in the sampling chapter. I think maybe just for a slide or two. But for sampling with replacement, I'll have an example that, suppose I have a fishbowl that is full of 50 names. And suppose it's the names in the classroom. And so if I draw it with replacement, I'm saying, no, I want to get 5 names out. So I take 5 names out. 5 names, I record them, but then the 5 names go back in the bowl, into the fishbowl. And so when I'm doing a sampling again afterward, I'm still having 50 names instead of 45. If I was doing it without replacement, then I took 5 names out of the fishbowl, then if I took some of these out, and if I took 5 out, then there would be 45 remaining. The same thing would be like if I called on one of you for a question, and then you didn't have to answer a question for the rest of the class, that would be sampling without replacement. And so depending on what probability problem you have, it will either be mentioned that you're drawing it with replacement or drawing it without. So like if I was, like with those names, you would know kind of what to use with or without replacement. And so I just want to have an example here of winning that lottery, still using the 3-digit kind of combination rule here, 000s to 999s. And event A is the winning number is 956. Well, if you assume that everything is likely, it's just 1 out of 1,000, it's just one number out of those 1,000 possible numbers. However, if you have different events that classify it, you can identify it, you can like break up the problem, right? So, and this can help them think about other problems too. So let me raise this up here. So event A is that it's 956. And obviously since there are 1,000 here, it's just occurrence out of total, which is just 1 out of 1,000. However, you can have B1 be the first digit's 9, B2 be the first digit of 5, second digit of 5, and B3 the last digit is 6. And so this happens 1 out of 10 times, this happens 1 out of 10 times, and this happens 1 out of 10 times. And so to figure out the total probability 4 having 956, you would multiply these all together, and you just get 1 out of 1,000. So here there's more than one way to figure out a probability besides having all of the total outcomes mapped out. You can just see and split it up into subproblems. Another example of this is this friend problem. So will Sean's friends be there for him? So this person, Sean, has 3 friends to call to wake him up. And the probability that each friend will call is 0.7. And so, three friends might call Sean. And then each friend has a probability of calling of 0.7. So what is the probability that none of them will call? Well, I can either do the first statement up there, which the probability that that any will call. So at least one is the complement of none. So probability of none. Probability of none equals 1 minus the probability that at least one will call that. And so just thinking about that, if so it's 1 minus the probability of none to call is the probability that at least one. And since we know from complements, 1 minus the probability of A complement equals the probability of A, we can use the same thing down here. And so the probability that none of them will call is doing the friend 1 won't call, friend 2 won't call, and friend 3 won't call. And so this is just 0.3 to the third, which is 0.027, and you figure out 0.973. However, if you just wanted to do a long and drawn out way of it, you could do all the different scenarios. So you could do, well, 1 calls, 2 don't. So, 0.7 times 0.3 times 0.3, and then any of these. So this is the scenario where 1 person calls. So this is 1 person. And then you have to think about the combinations with it, and since there's only 1 here, there's 3 combinations with that. You could think about 2 people, where you would have 0.7, 0.7, 0.3. And there's also 3 ways to permute this. And then you could do where 3 people call, and there's only 1 time where this happens. Now, would you guys rather try and calculate this, or would you rather try and calculate it this way? Right, because you got to do 1 math step instead of 7 on this side. So when you're thinking about these problems, think about how you can view it in the complement way. And I guarantee that there's a question on the quiz that's shaped up like this. So think about that when you go to the problems. Yeah?
How do you get like the 0.973 on that side? Like would you have to
you would have to multiply all these and then add them all together.
Is
So-
all three people or just one?
Add all 3 times that this can happen, because there's 3 ways in which one person calls due to the ordering here. There is 3 ways to order it here. Now this is doing 3 choose 1 ways, 3 choose 2, and 3 choose 3. This is 1, this is 3, this is 3 in this case. And so however, if you use the complement rules, you can figure it out like this. Any other questions? Alright. So let me go ahead and move on to something called Bayes' rule. Have you guys heard of Bayes' rule before in any of the previous classes or anything? 1 or 2 of you? Yeah. Essentially, this is a pretty popular rule. It sets up like a whole field of math. We won't talk about the whole field of stats for today. We'll just talk about the rule. And so it's used in the case that you want this, but you only have this quantity over here. You only know what happens if you know B, and then what the probability of A is. And so essentially, what you're using for this is that since we know P of A given B equals this, we can extract this probability and put it into multiple pieces, like what's down below. So we know that if we multiplied across here, if we multiplied P of B across, we would just get the intersection between the 2 events. And so what I can do is I can drain this out, and I can consider all the complements in that case. So what if A happens? So this is for A, but this only gives P of A B. But this also gives P of B given A complement minus P of A complement, and this gives me this. And so in the type of Venn diagram case, so we have S here, and we have A, and we have B. And so if we have the intersection between A and B, we have this right here, this whole section. And that's good, but we need to find the other section of P of B, which is all this. And so A complement is all of this outside space, including everything in the sample space, right? Because it's everything not in A. And so since it's intersected with B, you get this cross-empty space, and you can see that all of P of B is filled. So we can write out Bayes' rule in terms of this, and now I can use, so this would be the opposite case for this. Yeah. So we know P of B given A, which is this here, and now we can figure out this probabilities and these over here, just to figure out what P of A given B is. And so we'll see an example of this on the next slide. So this is, so what's the probability that a person has a disease given that the test was positive? And so in this case, and in these word problems, you got to map out, well, what's A, what's B, what's the opposite of A, that type of thing. So, A is the probability that Alicia has the disease. And B is the probability that the test is positive. And so you want to, A disease, yep. And so A complement no disease. So what would B complement B in this case? If the test was positive for B. Well, it'd be negative. So BC would be the test is negative. And so we already have these proportions out of here. We know P of A is 1 out of 1,000. P of AC then is 1 minus that, which is 0.999. And so we have all these underlying probabilities here. So I'm going to write them on the board just so we're following. Let's see, 0.95. P of B given AC. 0.05. So BC AC is 0.95, and this is 0.05. And so we can see, using the math up here, I can do it on the board, but essentially we're using all of these right here and plugging it into this equation. So we want to figure out, based on this problem, P of A given B. But we don't know that yet because we only know these and this conditional probability is over here. And so we can figure out what P of B is. So B given A is 0.95, and then P of A is 0.001 plus B given AC, which is 0.05, multiplied by AC, which is 0.99. And so just what they have here, I'm going to bring up a calculator real quick. So this part here is 0.04995, and this part here is very small. 0.0095. And then when I add these together, more 995, I get that P of B. So what we have is that P of A given B and now that P of A and B, which is 0.00095, which is up here, because we already calculated this portion. So and so it's just 0.00095 divided by this, which is 0.019 or 1.9% or 2%. And so just from figuring out what these were given before, the P of B given A, BC given A, these types of ones, we can figure out what the probability that Alicia has the disease, which is A, given that her test was positive. So, in this case, 0.0. All right, a little bit long-winded. We got through. We can also use this doing two-way tables. So we talked about two-way tables a couple weeks ago when we were talking about conditional. When we were talking about categorical variables in general. But we can also use that to understand probabilities in the table. All right. And so we're having this teens and gambling thing again. And so in this, we have 49.1% ninth grade believe it says no boys. Gender split. So boys, and then 50.9% girls. And so here, since we found before that it was 22.9% boys who gamble, and then it was 4.5% of girls, that if we had 100,000 teens, that we would have approximately 49,100 boys, 50,900 girls, and so we would have a certain number of gamblers from this, given 100,000 teens if we extended this study. And so this is just multiplying the probability that they're a gambler by how many that there are to get a total sample size. So we can get into a table like this. And so once we get into a table like this, it's quite easy to calculate probabilities overall, because we can think about it like this. So we have, I'm just going to say G and G complement, because we have gambler, not weakly gambler. And then we have the event boy, and then not boy, which is girl in this case. And we have for here. And so we already figured out these row totals over here based on simply these multiplied by 100K. So we know these totals already, and then we can just calculate how many people gamble by doing column totals. 13, 5, 3, 5, 86, 4, 6, 5. And so overall there's 100,000. But what we can do is say, well, what's the probability of a boy and gambler out of these 100,000? And all we would have to do is take this number right here, this 11244, and divide it by 100,000, which this just becomes 0.112, and you're good to go from there. However, this helps when finding out conditional statements. So if you just want to know, oh, I'm only going to consider the group of gamblers. And now you know what your denominator is and what your numerator is. So probability of boy given a gambler. So if you know that somebody's a gambler, what's the probability of them being a boy? And so it's not 22.9% over here. That's not the answer for this. The answer is B and G divided by P and G. And so can anybody tell me what the probability of gambler would be in this overall? Because we have these column totals, we can just take this number, and this is 13,535 divided by 100K. And so in the numerator, we already figured out what the B and G is. And so from this, the really nice trick is that we don't even have to divide by how many there are overall. Because there's this part in the numerator, and this part in the denominator, they just cancel out. And this is what you're left for the probability of boy given gambler. All you need to do in this contingency table is take this number right here and divide it by how many gamblers there are overall. And so you can do this in any case. Suppose I wanted to figure out, what's the probability of girl given that they didn't gamble? Well, so probability of girl, which is B complement, given that they're not a gambler, it's the same thing as this. And since we all have the same overall total, what I can do is just take the total number of non-gamblers, which is 86,465, and take the cell where boy complement and gambler complement intersect. 48,609. And so there's the answer for boy complement given gambler complement. Does this make sense? The contingency ones are a little bit easier to understand than just having, text and everything straight up, because all the numbers are there in front of you. And so what you can identify is this is like all gamblers complement, all boys complement. And this is just total. All right. Another way to think about conditional probabilities are through these things called tree diagrams. And so there's a couple steps here, but I think it just helps if we have an example. Am I okay to erase this? You guys still writing this down? So here are the steps for the tree diagrams. I can go through these. Determine the first random circumstance and sequence, then create branches for any possible outcomes. Create a branch for each outcome, and then write the probability on each. And so we're going to go back to Alicia having positive test, have disease given positive test. And so that'll be the example we're doing next. Determine the random circumstance and append branches so you can keep on adding on. If you think about trees, you have a tree here, but you can think about that in terms of branches, where we have A or A complement, and then each one of these you can have B or B complement happen after that. And so this particular branch right here would bring the probability of A complement and B complement. And so you can continue this as many steps as you want to go along, and then determine the probabilities, you multiply across, and then you can add up the individual probabilities. So I'm just going to show this here for Alicia's possible fates. So what we have is this initial branch, which is A and A complement, which is given the disease, which is 0.01, 01, and 0.99. And so as a result of these, you can either have a positive test or not. A positive test or a negative test. And so in each of these cases, you know that this is 0.95 case. And so the only types of information I've written down so far is just P of A and P of B. And so I can multiply across to get what the intersection of the events are. So we have 0.00095. We have 0.0005. And we have 0.04995 and 0.04995. 94905. And so if you're doing it this way, you just want to make sure that they all add up to 1, because these are all the total possibilities you could have in disease. So the probability that they have a disease and a positive test is this right here. This is the probability of A and B. And the probability that the test is positive, well, you can add up all the branches where the test is positive. You can add this one and this one right here, because you know you have positive down here, positive right here. And so the probability that the test is positive is just the 2 added. These would be the conditional probabilities here. Yeah. So what these are put in here, we have B given A, which is this one, the 0.95. We have P given AC, which is this down here. How do I do it? Yeah. Am I doing it? Oh, wait, I put this down the wrong way. This should be 0, 5, and this should be 9. Okay, so I still have this right up here. B given AC, this is B right here, and you already know what this information is, A complement. And so the probability of B is the same thing as this branch, the first branch, plus the third. So this is just first branch plus third, which is 0.509. So just different ways of figuring out the same problem. We can also have, they have the disease given the positive test. So if you have the disease given the test, you just need to do 1 first, divided by 0.509, and then you get back the same answer of about 2%. So you can either do the mathematical way and just write out all the equations, or do it in this tree diagram sense. You can also do the same thing here with having sex and gambler, but I'll kind of let you review that on your own time if you want to go through it, ask me questions later on about it. And lastly, I want to get about using simulation to estimate probabilities. So I can actually do the same type of thing on a computer and just simulate all the possible scenarios that could happen. And this is kind of just like the easiest way to get this done. You just have to have some computer knowledge before doing that. And so I've showed an example of this, but you know, I'll ask you directly on the test to simulate 50 times this happening or whatever. However, if you simulate something n times, and the outcome that you're interested in happens in x out of those n times, of course the probability is just going to be x out of n. Like what we had for more probabilities, it's the number of occurrences divided by the number of times it total happens. So one case here is that we have 50 simulations of prizes from cereal boxes. So you have cereal box 1, 2, 3, and 4. And so suppose you get 6 boxes randomly, each with a 0.25 chance of drawing from it. But I don't want to just write out what the basic probability is. It's going to take a lot of math. Out of 6 times, it's going to be a lot of steps to write out, and so I'm going to want to simulate this. In this case, the book simulated 50 simulations of prizes from cereal boxes, and so it's the same type of like lottery number sense, but the probability of the event is that you have at least one of the 4 numbers. Well, at least one occurrence, I should say. One occurrence of the 4 numbers in 6. And so you can see here that all the bold ones have numbers between 1 and 4 for every single one of them, and they did this 50 times. and they figured out that it's about 0.38, and the actual is 0.3809. And so this is something called Monte Carlo. I don't think I'll get too much into it in this class, but essentially I can simulate this process, and the more simulations I have, the closer I get to this number. And so I am, yeah, there we go. All right. Let me make this a little bit bigger so we can see. So essentially what I have up here is just code. What the first part is that I'm just going to basically replicate what the book does. So I'm just going to replicate 50 simulations and check out what my percentage is. And so just to let you guys know, what one run of this in the bottom right over here, this is just like what we had before. So this is 4, 3, 3, 1, 2, 4. So that's just one run of me getting 6 cereal boxes. And I would win here because I have 1, 2, 3. And so I'm going to do this 50 times and see how many times I win. And so I have 1.38 out of here, but if I just run this again, I can get a different number. I get 0.4, and we're looking at the bottom right over here. So 0.4 here, continuing to get 0.4, 0.38, 0.44, and so on. However, if I ramp this up to 500, then you can see I'm getting a little bit closer. I'm not getting into this 0.4, which is so far away. And if I go to 50,000 and do this, I get pretty close to the answer every time, being 0.3804. So I'm only get like a tenth or a hundredth off, actually hundredths place off in this case. All right. Well, that's it for today. Does anybody else have any more questions? All right. Well, homework and quiz are assigned due next Friday, and then Monday will be an in-class activity.
Thanks, Katie. I appreciate that. Yeah, let's do that.